Hi, welcome back to Moose and Chemistry. This is electron configuration of lanthanum. Now, lanthanum is element number 57 on the periodic table. Right? So we're going to put 57. And its atomic mass unit is going to be 139. So now we want to know a number of protons. Well, the atomic number is 57, so the number of protons has to be 7. So that's what the atomic number represents. Since lanthanum is electrically neutral, we'd have to have 57 electrons also. So when you go AMU minus protons will give me, of course, the number of neutrons, right? So you go 139 minus 57 equals 82 neutrons. Alright, so we're going to put 82 neutrons down. Pretty snarly is what I have to say about that. Okay, so let's clean this mess up here. Okay, so now we're going to do our electron configuration. Before we do that, we have to remember that the S subshell can hold 2 electrons, the P subshell can hold 6 electrons, the D subshell can hold 10 electrons, the F subshell can hold 14 electrons, right? We're using the off-ball principle, which clearly states that we're going to put electrons in the lower shell first, and then we fill as we go up the levels, right? And we're going to use this by doing the diagonal rule. And the diagonal rule is a really great way of doing things. You just follow the red arrows right here until you run out of electrons. We got 57 of them, so let's go ahead and get started. So this would be 1s2. Okay, 1s2. 2s2. Snarly, huh? 2p6, 3s2. 3p6, 4s2. 3d10, 4p6, 5s2. 4d10, 5p6, 6s2. Now, we're going to not put anything in for the 4F because lanthanum is not in the F block. It's technically in the D block. And you have to remember the periodic table, even though it looks two-dimensional, it's actually three-dimensional. It has different levels to it. So we're going to buzz over that. I'm going to put in a 0 in for that. And we're going to call this 5D1. Right here. I'm going to call that 5D1. All right. Now, I know it's pretty weird, but that's the way it works. Okay, let's do our orbital notation. Remember, orbital notation is Hund's rule. And Hund's rule will clearly state you have to put an up arrow in every suborbit before you do a down arrow, right? Okay, let's do that. So up arrow, down arrow, up arrow, down arrow. Watch this, 2px, 2py, 2pz. And go down, down, down. Classic Hund's rule right there. Up and then down, see that? Okay, we're just going to go ahead and fill these guys again until we run out of electrons. And remember, it's important to keep count of your electrons. Okay. Pretty snarly. This is a lot of fun, actually, if you think about it. We can get the electron configuration, orbital notation, noble gas notation, and quantum notation right. Wouldn't that be a great game to challenge your friends with? I think it would be. Wow, that would be actually cool. All right, so let's look. Okay, now we're getting close now. So we're getting 5s. Okay, so now we're going to start mining our P's and Q's, as they used to say. And let me show you what's going on. Because I'm going to explain to you why that's 4f doesn't have any electrons. Just about there. Okay, now we're there. Now think about this. Lanthanum is in the D block, right? But it only takes 10 electrons to fill the D shell, and it takes 14 electrons to fill the F shell. And since we're still technically in the D block with this particular element, we have to skip over that. And we're going to put 1 electron. Okay, now let's look at our noble gas notation. Now, what's the nearest noble gas to it? It's going to be xenon. So we put Xe, and then we're going to write this right here. Now, some people leave that 4F out, but I'm not going to because I need to remember that it's really there. So we go 4F0, 5D1, 6S2. Very, very important to remember. All right, now let's look at Pauli's exclusionary principle in the quantum notation. Pauli's exclusionary principle clearly states that no two elements can have the same set of quantum numbers, right? Okay. So let's look at our principal quantum number, n, first. Hey, wait a minute. I know it looks like it's in the 6th period, right? But it's not, because it's a D block element, right? So you go n minus 1. So you would go 6 minus 1 would give me 5. So the n block number is 5. And since we know it's in the D block, the angular momentum number is 2. And the magnetic number, it's going to be the first element in the D block, so it's going to be minus 2. And then this last arrow is going up, right? Okay. So it's going to be 1/2 positive. And that's it, guys. You be snarly, and we'll see you back here at Musin Chemistry.